I introduce you the lunar laser ranging. The first part will be the history. After the difference between LLR and SLR, the technique is the same, but not this, we don't use the same system exactly, because after I will speak about the LLR network, and Doug will continue with the contribution of the science and the new challenges and the next generation of retroreflectors. Okay. The lunar laser ranging became possible after the Apollo 11 mission placed the first reflector on the moon. After five reflectors has been placed on the moon. The first one was Apollo 11 in 1969, followed by Lunar 17 mission, and he deployed on the moon the Lunar 1 rover with a retroreflector also. After Apollo 14, Apollo 15, and the second one, Russian rover on the moon, Lunar 2, with also reflectors on board. Okay, here you see the description of the reflectors. Apollo 11 is a square with 100 corner cubes, the first one. Apollo 14 was the same type of corner cube and the same number of corner cubes. On Apollo 11, we have 300 corner cubes, and in fact, this reflector was used as a reference before to try to range on the other reflector, because it is 3 times more efficient than the two others. On the Russian missions, the reflector was in this part, and it's a bigger reflector, only 14 reflectors, and it works during the night on the moon, but it's difficult to use it during the day because there is a deformation due to the temperature. Okay, as present John, the link budget is power 4 of the distance. And if you range on the satellite between 300 kilometers up to 36,000 kilometers, on the moon, you range at around 400,000 kilometers. So the link budget is about 10 power 4 less than in SLR. In this case, if we have at the base the same equipment, we need a larger telescope. We need also to have a more powerful laser and very good pointing, very quality of the pointing of the telescope. And in all the cases, we are in single photon detection. I think in Apollo's station, they are in multi-photon, but it's a very big telescope. It's the most beautiful station we have. It's in New Mexico, and it's at maybe 300 meters of altitude, or 200, I don't remember, 3.5 telescope. It's okay. Okay, donc we need the larger telescope as possible, as you can pay, in fact. And if you have a big telescope, you have a minimum divergence, and the spot on the moon is small than with a little telescope. Donc you need a big telescope. At the reception is the same. If you have a big telescope, you can receive more photons than with a little telescope. And you need also a good pointing, because when you point a reflector on the moon, you need to point with the arc second at the arc second level. If you move your telescope from 1 arc second, you have no echoes. So it's not like on satellite. On SLR, you can open the divergence of your station, and even sometimes the prediction is not very good. And it's not a problem to have a big divergence, because you continue to have a good return in your telescope. With the moon, it's not possible. You are always the most parallel as possible at the emission. And the tracking also need to be at 1 arc second in 10 minutes. Just to have enough echoes in 10 minutes. So in 10 minutes, at the beginning, it was around 100 echoes with a 10 hertz frequency of the laser. And now with Apollo is in multi-photon in reception. Okay, you have a lot of echoes. In the other station, we are in GRASS. Now we change. I don't know if we have time. Yes. Alors, first one is when we choose the most powerful laser. On the lunar laser ranging, the limitation of the accuracy is due to the accuracy of the reflector. Donc we don't need to have a pulse width less than 100 picosecond. It's not necessary at that time, but Doug represents you new reflectors, and at that time we will need to change the laser. But now it's not necessary to have too short laser. It's better to have little bit wide laser, large pulse width, and more energy. Well, okay. One new thing new from the last 10 years is now we try to range in infrared. In the past, it was difficult to find APDs, avalanche photodiode in infrared. The accuracy was very bad. And now it's possible to buy a new APD. The accuracy is not as good as you can find in green, but it's enough to range, and we have a lot of energy in infrared because the laser is only in infrared. The first frequency of YAG laser is infrared, and if you want to make green, you lose the half of the power. You have 2 times more photon in infrared than in green. You have less noise also in the sky in infrared. Donc with all these improvements, for example, in GRASS we had a result. The number of echoes in 10 minutes was around 100, 200 at the maximum of 400. Now in infrared we can reach 800 until 1000 echoes in 10 minutes. There are 4 operational stations: Apollo, the Apache Point station in New Mexico, GRASS in France, Matera in Italy, and the new one is Wetzel. Wetzel, it's very good because it's very accurate station, because due to the laser, it's a very short pulse laser, and the first results are very interesting. And some other stations are in development, like in China, in Russia, and in South Africa. Now I let my place to Doug. He will continue to present you the other aspect of the contribution of the science and so.
Okay. I've got a thing. Oh, here to change. Okay, as was mentioned, there are 5 current reflectors on the moon. In some ways, that's enough to get the center of mass and talked about general relativity. On the other hand, it's way too few to do the mapping of the moon and to get a good cylindrical coordinate system. These are still working after 50 years, the only experiments that have continued since Apollo. Almost daily ranging occurs, and what you might ask is why do it more than once? The reason for doing it more than once is that by looking at that long train of measurements, you can extract different frequency components, and typically those frequency components are related to different aspects of physics, of general relativity, of Earth, or in the moon, its interior of the moon. So you've got the long data. That analysis continues. Jim Williams in JPL, who was on our original team, continues to do this analysis. There are teams in Germany and in France that are doing parallel analysis in order to have a continuing and, again, as I mentioned earlier on satellite ranging, the ability of different groups to look at the same thing allows extraction of systematic errors. Okay, as far as the physics, there are many things that come out of this, many tens. So I'm going to concentrate only on a couple, just to give an example. For the relativity, LLR has the best measurements of these parameters. One is the strong equivalence principle from Einstein. That is, the physics in different frames is the same, whether they're moving or not, whether they're in gravity or in space. The rate of change of big G, which was just mentioned, that whether it's big G or whether it's the mass of the Earth, is tiny. If, for the entire length of the universe, the changes are at the same rate as we have measured in the last 50 years, it's changed less than 0.5% in the entire length of the 14 billion years of the universe. The n squared, the 1 over r squared behavior of gravity in the vicinity of the Earth-Moon system, again, we're able to get a very good handle that agrees with the 1 over r squared law. The weak equivalence principle, that's the two things that I drop fall at the same rate. I'll talk a little bit more about that in a moment. And finally, this is one of the few experiments that looks at moving matter. Almost all the normal tests of general relativity look at essentially static, unmoving objects, masses. And there are 3 experiments in this. One is the gravity probe B, other is Ciuffolini's use of Lagios. The LLR is a factor between 10 and 100, more accurate than either of those. Oops. Okay, let me look at this one particular science area, which at the bottom, I'll tell you why I think it's the most interesting. This was essentially our history of Galileo's dropping things off Pisa, the Tower of Pisa. Unfortunately, what Galileo derived the weak equivalence principle was from other experiments. The Tower of Pisa experiment was something added by his biographer. He never really did this. But the measurements we make say that Einstein was correct, that different lead and wood fall at the same rate. We measure that by looking at how fast the Earth and the Moon fall toward the Sun. So that all these bodies measure at the same rate. But to me, the most interesting aspect of this is that because in our bodies, in the Earth and Moon, there's a lot of gravitational energy. What we found is that not only is it hard to push a piece of iron, but it's equally hard to push gravitational energy. In other words, the gravitational energy contained in the Earth makes it harder to push just a bit more than just its mass. And it's a unique experiment in that no one else has touched that. All right, I'm now going to go into talking about some new retroreflectors. The question is why? As you saw in a previous talk, we had large errors in the early days, but for the last 2.5 decades, we've had essentially no change. We're down at the centimeter level, and we're not improving. Question is, why does this occur? And the reason is, if we look back at the Apollo array, it's an array, and the moon, you think you see the same face of the moon all the time, but really it changes a little bit, about 10 degrees, so that if you look at the right time, you can see more on this corner or more on this head. That means our array is tilting. And so in the crude, or in the pedagogical sense, we don't know whether the photon came from the far corner or the near corner. And that is the fundamental reason for this spreading out like this. So the question is, how can we get around that? Well, the retroreflectors on the Apollo were like this. The way to get around that, I can pass that around, is to have one reflector that's large. And the one that we're working with is of this size. This is really not a flight one, but it's actually one that I bought for the McDonald's station back 50 years ago. But by having one reflector, we've gotten past this libration problem. So, and again, we pass that around. In order to do this, the package we put together looks something like this. And here's the corner reflector. And we have a housing which is sort of shaped like a corner reflector. And then it's set. This is a model, full size, of what we would like to put on the spacecraft or on the lander. I don't, well, yeah, we can pass that, but be a little careful with that. It's the only one I have. So the reflector arrays are still working after 50 years. They're continuing to produce new science, both lunar science and general relativity measurements to look at the difference. These next generation lunar retroreflectors, the NLGRs, which are being passed around, will improve the ranging accuracy by up to a factor of 100 compared with what it is today. And it's limited only by the ground station, primarily laser pulse length, and the atmosphere. In addition to what John mentioned about problems with the atmosphere, we have another real problem. And that is, if I measure temperature and, mainly pressure, temperature, and humidity here at my station, that means that I can do a very good prediction when the moon passes overhead. The problem is all of our stations are at latitudes that are around 40 degrees, so it's always like this. What happens if 7 kilometers over there, the pressure is different? This produces a wedge in the atmosphere, and that means errors of the order of a millimeter. And so pushing beyond a millimeter means better observatory hardware and better modeling of the atmosphere. As far as where we are right now, NASA has selected the University of Maryland to deliver 3 of these NGLRs, and they're to go to the lunar surface in 2021, in 2 years, a little bit less than 2 years, on commercial carriers, like you may have heard, Astrobotics, Moon Express, groups like that. Finally, why push for greater accuracy in this? Well, at present, we only know about 5% of what the universe contains. A large part, 25% of the order, is dark matter. I don't know what dark matter is. No one knows what dark matter is. It's just, we can see some effects, and so something's going on. Likewise, a few years ago, by looking at distant supernova, we found that galaxies are moving away from us too fast. Once again, there are lots of theories, but no theories have gotten to the point of producing reasonable measurements. And so almost all of the universe is unknown. And so at present, we come down to the fact that from my point of view, what we do is we're trying to push the measurements and to see where something breaks down. For example, quantum mechanics and general relativity do not fit. One of those is going to break down. And so the question is, how do we find out what that is? Thank you. That is true, but that means you have to have very many photons. Tom Murphy normally has of the order of 1,000. That means that stations without this very large telescope are not competing in that. What this will do will mean that every photon that comes back is accurate, and that in turn will lead to stations like Wetzel. Wetzel currently is ranging to the moon, but they have the spread. What the NGLR will do, it will allow Wetzel and hopefully other SLR stations, because the advantage of SLR stations is that because they typically have larger signals, they have shorter lasers, and they have better timing, even though they normally have smaller apertures. And so this will encourage or allow SLR stations with small apertures to participate in the lunar ranging, which in turn means that we can have the advantage that SLR has to find out, oh, so-and-so didn't calibrate exactly, and so we can correct him and get him back on the network. Your question requires me to say a little bit more accurately. What happens is that when we send up a very narrow pulse, what comes back on successive shots is a spread. And that spread is determined by what I mentioned, the tilt. But we can't model and say, oh, this one that came off a little bit ahead of time must have come from, we don't have that information. The desirable aspects of the ground station would be about a 20 picosecond laser pulse and timing electronics that was comparable, maybe 10 pico. And MET station that is good enough to provide that kind of millimeter accuracy, which I think what John mentioned is probably enough. Then the other part of that is going to be, can we determine what this atmospheric wedge is? And that would allow us to push below 1 millimeter. And there are groups that are looking at how you use MET stations around a LLR station, or actually they're doing it for satellite. And the wedge is equally necessary for satellite ranging as it is for lunar, to determine that from local MET measurements. Or the other is we're hoping to look at an instrument that we built years ago at Maryland to actually directly measure what the wedge would be above the station. I would love it. Are you going to take mine up there? No, that would certainly help, because those are clearly distinguishable returns. But at present, it has been, for me, a 15-year process to even get 3 of them up there, which is happily what NASA bought into, because I argued that general relativity requires me not to know where crater so-and-so is, but it requires me to know what the center of mass is. Because of the librations, I have to have 3. But the hope is, since these are relatively inexpensive per unit, that they could ride on many spacecraft. That unit that's passing around is about 1.2 kilograms, depending upon what the mounting structure is.
Thank you.